Okay, so my physics professor thought it would be a good idea to ask us to demonstrate the formulas that we use to calculate electric field on highly symmetrical figures, and so I need to memorize those, or rather, yeah, memorize, because I already saw him deducing those equations, so it's no longer a deduction of my own if I have some tips on how to solve them. But anyhow, electric fields. Let's say you have a charge here, a small charge, and you have a bar over here. All right, I'm gonna try to draw a bar to the best of my abilities, which are not impressive at all. Let's say the ball, or like the tiny particle that I have, it's from a distance of a to the closest part of the bar, and the bar itself has a length of L, and the bar is charged, equally charged throughout its whole length, which means that if I get a small part of the bar here, it's going to have the same charge of the small part that I look here, so it's equally distributed charges throughout the bar. And I want to know what is the electric field generated by the bar that this bar exerts on the particle, the red particle. Well, to do this, we're going to use some calculus tricks involving infinitesimal elements, as well as a bit of integration, but it's not that complicated. What we do need to have in mind is something that my physics professor likes to call a water container theorem, you could say. It's just a fancy way to say that, okay, if you have a very small quantity of water, say a droplet of water, and you have a water reservoir here, like very big one, with a huge volume of water here, what does this droplet of water has in common with this reservoir? And it's the density. So the density of this water over here is the same density of the water in this tank, because they're essentially the same thing, right? It's water either way, so you got to look with the same mentality to the bar. The density of charges in this bar is the same density of the charges in the small piece of the bar. Okay, so in other words, sigma, which is not an internet meme, okay, it may be, but in this case it's just the quantity of charges, so like charge by length of the bar, is a constant. Okay, so this is important to know. But anyway, say I will get so using this, I will get a small part of the bar over here. I'm gonna call it dx. Right? Very small infinitesimal part. So we can say that infinitesimal electric field equals Coulomb's constant times dq over x squared. X being the distance from this tiny part of the bar to the ball, right? Doesn't really matter. And well, you gotta integrate that. However, how do you integrate something that is not a constant in relation to another non-constant variable? Well, this is where this theorem comes into place, because you could write this as equivalent to sigma equals dq over dx. As I said, the density remains constant. Therefore, you could write this as the following equation. K, instead of writing dq, we can isolate dq here. It will be sigma dx equals dq, equals dq. So really, we can just write sigma over here, dx over x squared. Now it's much more manageable to integrate both sides of the equation. And if we want to integrate both sides of the equation, integral of dE is just E, right? And then we have this over here, q sigma dx x squared. So we know that k is a constant. It's 1 over 4 pi epsilon 0. And sigma is also a constant. It's the main thing that, allowed us to get here. So we can just put them out of the integral. So it's k sigma integral dx over x squared, which is much more manageable to integrate. Every Calc 1 student should be able to do this, no problem. And the physics from now on, it's really over. I mean, so it's k sigma. One thing you need to understand here is that we're integrating from a. So see, this is a xy plane. So we have an xy plane here. We're integrating from a to a plus l, right? So it's a defined integral. As a defined integral, we need to put here a to a plus l, and now we can do this, no problem. So this is just dx, this is 1 minus 1 over x, right? Did I do that right? Yeah, I think I did. Evaluated from a to a plus l, and voila, it's this is all there is to it. Lambda, sigma, and this will be 1 over a plus l minus 1 over a, and then we can just substitute sigma for its original calculated way, which is k over l, so sigma is k over l, and multiplies 1 over a plus l minus 1 over a. I think I did something. Yeah, it's the other way around, because it's going to be minus. Is it? Wait, it's going to be. Oh, sorry, I think I made a mistake here. It's 1 over a minus 1 over a plus l. It's because there's a minus here, I got confused. So instead of being the bigger number minus the smaller number, it's going to be the smaller number, which is a minus I mean, the fractions are the other way around because it's under the numerator, but you understand what I mean, probably. Hopefully. Oops. So let me just fix this real quick, and there we have it, 1 over a minus 1 over a plus l. There you go. And with the electric field, you can of course calculate the force being a times q. So you just plug q into that and you be happy, and that's how you deduce it. Hopefully this is what my professor wants me to do on the exam. So this is what I will try to do. And now we do the ring. Yes. The ring over a certain distance z from a particle. So we have a ring here. Oh, perfect. And say you got a particle over here. And I will call this height over here z. And the ring has a radius of, I don't know, like a again. You know, I'm pretending I'm coming up with these variables, but they're very well established on the deductions of the proofs. But anyway, something interesting here on the ring is, say the charge is positively charged, and the ring is also positively charged. What are the consequences on the of the electric field? Well, it's gonna push the ball outwards. It's gonna like kick the ball sort of in this direction, right? So, you know, we gotta calculate this electric field, like this, the electric field that is pointing in that direction? And the answer is no, because, well, you are correct. There are particles here that are exerting an electric field on the bread ball, on the bread particle over there, in that direction. That is correct, but at the same time, there's also a particle here that is causing the same effect, except mirrored, so it would be something like this. You might say, well, they cancel out, and I say, not really. Partially they cancel out, because you can write this as a component of EY, EX. This is also EY, EX. So you see what I'm getting at? These two cancel out. So the resulting electric field, it's only going to be upwards, right? So let me just represent that real quick. So what we're interested on is this EY, and EY, it's only going to be there's only a force on the vertical axis. This is what I truly mean. And say if I have the distance from the ball or the particle to, say, this particle over here on the ring, and I call this angle over here theta, I can say that the force EY being this E, equals EY equals E cosine of theta. So we want to calculate EY, not just E, because the EX component cancels out. So that's something that we got to keep in mind for the ring, just for reasons. So same thing with the bar. We can say E, the electric field, sorry, dE y equals to K, that's always there. dQ, again, we're looking at a small particle on the ring exerting an electric field. Let me close this real quick. Yeah. We're looking at this as a small particle on the ring is exerting the electric field on the red particle that we are interested in, that we're actually analyzing on this problem. Q over what distance? R. Probably a bad choice of name, since R is more suitable to be the radius, and you should probably call that A, but whatever. Over R squared. But by Pythagoras, I think that's how you pronounce his name in English, Pythagoras. Yeah, probably. We have a theorem that says that R squared equals, of course, A squared plus Z squared. It's square root of that. It's a square root of that, but R is it's times itself, so it's going to be this. So you don't have to worry about the exponents right now. Times the cosine of theta, because we're interested in the y component. So dEy, which sounds like do it yourself, but it's just the electric field on the horizontal axis, will be simply K dQ over this, right? But we could potentially write cosine of theta as in a better way. So cosine is the adjacent side over the hypotenuse. So it's just gonna be Z over R. But who is R? R is just Z squared plus A squared to the power of a half, which is a fancy way to say square root. So dEy, we could combine the numerator, the both fractions, since they're multiplying, we can combine the exponents of the numerator of the denominators and do this equals zk dq over a squared plus z squared to the power of 3.5. And then we integrate both sides, and the integral of dEy equals ey, which is fine. And then we have just a bunch of constants, which is going to be zk over a squared plus z squared square root of that cubed times the integral of dq, which is just going to be q. So ey, Jesus fucking Christ, ey equals zk q over a squared plus z squared to the power of 3.5. So that is the electric field on the horizontal axis, which again is the only axis that truly matters to us, since the horizontal axis will be cancelled out. In this problem over here, we did not use the water reservoir theorem that my physics professor likes to call it, but you get the sort of idea. It's not really complicated. You just need to play around with the variables and infinitesimals to get the right result. Now, I will say, this is going to be weird for me to remind how to calculate this. But there are more figures, so there will be a part 2, maybe a part 3 to this, because I need to calculate the disk. The disk. I also need to calculate when this red particle over here is close but not on the center, because on the center the y component is 0, and we saw that the horizontal component is also 0, so there's no electric field in here. However, if you're very close to the center, some interesting stuff happens, and I gotta say that on another video. But there's also the sphere that Newton proved. It's not a sphere, it's like a casket, no, a shell. It's an empty sphere, so a shell you put up, if the shell is charged and you have a positive charge here, the field inside of it is 0. It's Faraday's. Fuck, I don't know the name in Portuguese, but I would assume Faraday's cage or something like that. But outside, it does have one, and you can pretty much pretend this is a single point instead of a shell. But anyway, this video is, I'm extending the video unnecessarily. That's all about it. Thanks for watching, and see ya.